So we look at now, algorithms for big data, where somehow I'm going to assume your data is coming from read-only memory, and let's say for now I'm going to say my additional space is limited. It may not be all the way to constant. So let's go back to our algorithm for finding minimum, maximum, second maximum, min and max, and so on. So suppose the data is in read-only memory. I think it doesn't matter for us, right? Because how much extra space do we need to find the min? Let's say. So you have your input in an array, and how many extra variables do you need to find the min? One, because you just store max or min. Maybe a counter. There is an I for the for loop. There is an I that's going from 0 to n minus 1. You have to take that variable I as another variable counter, and max as another variable. So constant space. You can find min. You can find max. If I want second max, okay, so two variables plus a counter 3, so I can do the same thing. But if I want the kth max, then if I apply the same algorithm, it is just like k space plus the counter. Okay, remember that k smallest we remembered, and then thankfully the whole thing works in read-only memory. We didn't really go and touch and modify anything about the input, but we stored some k stuff, and new element comes, and we did some modifications in my additional space, which is fine. But uses k space. So in particular, if I want the median, right? So what's a median? This is the n by 2th smallest element. So in the sorted array, which will be the element which is in the middle? If I apply the same algorithm which we saw the first session, you'll need some order n space, which is too much. So the question I'm asking is, I want to find the median, and I have, let's say, constant space. Okay, maybe one or two variable, 5, some constant independent of n is the amount of extra variables you're allowed. I want to find the median. Let's think of some algorithm. I don't care about the time. Let's see, can I find some algorithm? Why is, if it's not a read-only memory thing, I can sort, arrange in the whole thing in sort, apply some heap sort or something, order n log n time. In fact, heap sort is very good on space, right? I want you to sort of reflect back on it compared to merge sort, which is also an n log n algorithm. Heap sort, you can build your heap internally in the array without any pointers extra, and then you can keep delete max and do so on and so forth, and everything can happen inside the array. Okay, so let me write it. I want you to just go back and check and understand this. So I'd say, if not read-only memory, then you can apply heap sort and pick the middle element. So that's like an order n log n time. Right, I'm already moving away from linear time, which I said you can actually find the median in linear time. The naive algorithm takes a lot of additional space. There are algorithms which can find the median using constant space and so on. Okay, I don't want to get into that, but can be done. But based on your algorithm's knowledge, if I just apply heap sort, I don't need any additional space except some constant number of pointers. Finish your sorting in the array, pick the middle element. That's one algorithm. But I can't do it in a read-only memory. So now I'm asking, so here is our puzzle, right? Think of it as a puzzle. Don't worry about, algorithm, I haven't studied. You're given some n elements in an array, and I give you 1 or 2 or 3 variables. I want you to find the median. Let's not worry about time for now. What can you give an algorithm? Then we'll analyze the complexity. Not very difficult at all. It's completely easy, trivial algorithm. No, don't confuse. Median has nothing to do with the values of the input. Right? So it's not, median is different from average, and that's not what we're talking about. We are talking about the element which is larger than half the other elements and smaller than the other half. That is the element you're looking for. Okay? So it's a standard median element. So I mean, or if you say, let's even say I want to find the kth smallest element. I mean, to avoid confusion about this median business, let's say I want to find the kth smallest element for some large k. Okay, I only have constant space. 2 variables, 3 variables I allow. How much time do you need? What would be an algorithm? Let's start with some simple brute force algorithm. Some for loop, something, right? So, not a difficult question at all. I wanted to think from scratch without resorting to some big buzzwords and known algorithms. N-1 comparison?
Whatever the basic algorithms we do for finding minimum or maximum.
Right. That only works for minimum or maximum. I want to find the kth smallest.
We can do in place sorting, then we find the middle element.
I can't, it's a read-only memory. That's why I said, if it's not the case, then I just told you the algorithm. You do in-place sorting, exactly. Heap sort, there are in-place versions of merge sort you can do. So just what is the algorithm? So the algorithm, I mean, if I say it, you will be disappointed. That's all. So I don't want to say it, because then you will lose the fun, right? I want one of you to tell me the algorithm. Yes. I mean, think of, whatever you are used to. If you are used to loops, think in terms of for loop. If you are used to some pseudocode kind of thing, I have a list of n numbers, and I want to know which is the kth smallest element. I am not bothered about the time. See, this is a hint. Take whatever time you want. I don't care. But I just give you space. There are only few variables you can. Huh? Give me the algorithm. Recursion, oh my god. That's too complicated to me. Yeah.
So take streams of data in size of k.
Okay. I'm given only 2 variables space. Okay. So we'll take stream. That's the kind of algorithm we did. If I have k space, then I told you how to do it in the morning. So, you really want me to tell you?
Use a counter.
Yeah, counter is a variable, sure.
2 counters, low and high.
Okay.
And iterate and just check whether the pointer which is at low is and was basically will compare both the counters. Will initiate one from 0th index and one from the last index. And then we'll just check on if they are like if the high counter is greater than.
What is the counter? What are you counting?
Basically, we're comparing, and if it's lower than basically the one we're iterating from end, we'll check if it's less than the.
If what is less than what? I mean.
Basically, we take 2 counters.
Okay.
One will initiate from the beginning of the
Okay.
array, one will initiate from the last.
Okay.
Last element.
Hmm.
So basically, we'll check if the last element. Basically, we are trying to sort the array. So we'll check if that counter is lesser than the low counter which we initiated from the beginning.
So when a new when you see a new element, what do you do? I want to understand.
So basically, sir, if we'll just swap the elements so that we can sort
Okay, so let me try yours.
So I'm thinking that we are processing every element once through the whole list, and if that element is higher than number, we will increase the counter by one. So when the counter reaches k or k minus one, then we have gotten the k element.
Great. So, how many people followed it? So, see, I want to know, is this the kth smallest element? What is the kth smallest element? How many elements should be smaller than it?
Smaller than.
K minus 1 element should be smaller than that element, and everybody else should be bigger than that. Can I not find, suppose I want to know, I pick one element. I want to know, is it kth smallest? What do I do?
Check if there are k minus one elements.
How do I check?
Check the whole list.
Check the whole list and do what?
Every element one by one.
Compare it with this element. So it's a one for loop. One for loop may I check, well, compare every element with this element and count how many are smaller. If k minus 1 are smaller, good, I found the answer. If not, I abandon this element, take the next element and do this, right? So one by one, right? Recursion in play. Don't think big, right? It's think from scratch. That's why I said. So I take the first element and I check, is it the kth smallest element? How do I check? One for loop of comparisons.
Once the counter gets bigger than k, then
Yeah, I have one counter which just, whenever I compare, and if something is smaller than this, I increment this counter, right? And at some point, I'd say if it's k minus 1, I say, hey, okay, exactly, this is the k smallest. If not, I move to the, so it's two for loops basically, right? It's two for loops. So it will be for I going from 0 to n minus 1, check if ai is kth smallest. That's it. And how do I check this? Well, for j going from 0 to n minus 1, j not equal to I, if aj is less than ai, let's say there is a counter called rank, I increment it, which is initialized to 0. And if the rank turns out to be k minus 1, then I know it's a kth smallest. Right? So it's now how much time does this algorithm take? O of n square. All of you should feel comfortable doing this analysis because otherwise you're going to be lost. So remember, I told you, using nice application of divide and conquer, I can find the median in linear time, order n time. Okay. But if you tell me it's not a read-only memory, you can do modifications, well, you can at least easily do n log n time. But now if you say it's a read-only memory and the space is limited, it becomes an n square algorithm. Okay, so these are the trade-offs. Okay, so what is this big deal about algorithms for big data is that space is limited, access is limited. Now we want to be clever about how we do things. Okay, and the big powerful tool that will help us is randomization probability, and that's what you're going to do as we go along. But right now I'll just give you a flavor of something which can beat n square for this problem. Okay. Okay, so this is so it's a very interesting, important question. If it's read-only memory and if I have only constant space, how best can I find the median? Can I improve to n square, n log n? Can I do linear time? This is a open problem. It's a research open problem. We don't know it. Okay, but what do I know? I'll give you some flavor of an n root n algorithm. Okay, I have this array in read-only memory. I want to find the median. Okay, so what we'll do? I take the first square root of n elements and find the median there. Okay, median in that block. How much time will it take? with constant space. Why? The quadratic algorithm I told you, the n square algorithm, apply it on this block. This block has only root n elements. So, in order n time with constant space, I can find the median. Let us say that happens to be this element, right. So, this is order n time. So, now what I will do, this is the step 1. So, let us call this x, right. Compare all elements with x. Okay. So, now I am going to apply some idea somebody was talking about this low high business. Yeah, you are telling about, right. So, what at any point of time, the median element I am looking for is between some, let us say, low and high. Okay. So, I remember these two elements. Okay. So, now this gets hairy. I do not expect all of you to follow it, but if somebody is up to it, let us spend 5 more minutes, I will tell you this algorithm. Okay. So, at any point of the algorithm, I am going to update this L and H, which means that the median element in the array I am looking for is between L and H in value. Okay. What would be the initialization I should do for L and H?
First index and last.
No, in value, it is not the index. In value, I want it to be between L and H. So, it is sort of like first and last, but yeah, minimum and maximum, right. Find the minimum in the list. We know we can do it in linear time with small space, and let us say that is L, right. So, that is min and max. Okay. So, find the min and max in the list and remember in L and H, and to indicate that the median element I am looking for is between L and H. Gradually, I will keep updating L and H. Eventually, it will be just one element and that element will be the median element. Okay. So, that is sort of the high level goal. Now, how do I update it? When I compare all elements with this x, I can count how many are smaller, how many are bigger, right, because it's a counter. And so, let us say I am looking for the median element or kth smallest element and something much smaller than k is smaller, then I know the kth smallest element is bigger, it is on the other side, right. So, okay, maybe I will switch to something. So, I found this element and I am looking for kth smallest element, and I found that some k by 3 are smaller and the remaining are here. Okay. Then where is k smallest? On the right, right. It is bigger than this, and now I have to also update my k. It is not kth smallest. I should look for k minus k by 3, which is 2k by 3 smallest element here, right. So, now I will update my L to this element and say, hey, the median I am looking for is now bigger than this element, not the median, the kth smallest. So, I will update this element. Okay. So, but remember, this x is already a median of some root n elements. So, already I know root n by 2 elements are this side, root n by 2 elements are that side. So, regardless of what it is, I managed to throw away root n by 2 elements, whether I go right or go left. Okay. And all this in linear time, constant space. So, overall, if I keep applying it, there are a lot of details missing. It takes you n root n time. Okay. and can even be improved. Okay, so I think I will not say much more about this problem. Questions? Yeah, so and this is a fun problem, right? I want to find a median, only constant space is allowed, and it's a read-only memory. It's not completely resolved yet about, you can also play this trade-off of, okay, not constant space, I give you a little more space, not n space, but maybe log n space, how much time it takes. These are all interesting algorithmic research questions about the trade-offs between time and space.